Hello, this is video I. In video I, we're going to talk about logical conditions. These are very important because they do things like control whether or not some statements are executed at all, and whether or not we execute some statements over and over again. We do that by setting up conditions and then test the condition to see whether or not we want to continue with doing what we're doing. That's way ahead of the game. First, let me define condition, also known as logical condition for short. Condition in C++ and just about every other language that exists. It's an expression that, couple of things, evaluates to true or false. Now, it's no accident I put the word true and the word false both in nothing but lowercase letters because those are reserved words in C++. C++ knows what true is. It knows what false is, just like it knows what digit 7 is, and it knows what a capital A is. True and false together are taken as single values of true or false, yes or no, 0 or 1. They also, I'll put in parentheses, usually. I think we discussed this at our class meeting Tuesday. Not everything that's evaluated as condition of C++ is something that we intend to have evaluated as a condition, so we better be careful. I'm going to say it usually involves a relational operator. I'll make it plural. Involves relational operators. OPR, apostrophe S for short. Which would be great if we knew what relational operators are. Let me put a table of them here. Relational operators, abbreviated, and what they mean. I'll put that over here. Not M-A, M-E-A-N-I-N-G. Having trouble getting going here. I thought I was all caffeinated up and everything. Double equals means is equal to. That's the one you got to be careful about when you're testing two. You know what? That's going to get our very first gold star. Double equals, that's an important one. If you want to see if two quantities in your program are already equal to each other, then you got to use a double equals. A single equals won't do it, and I'll show you how a bad thing can happen if I remember when I get finished with this table here. Exclamation point equals means is not equal to, abbreviated. Less than means less than. Greater than means greater than. Less than followed by an equal to, a single equal sign without any space between. All of that is one relational operator. That's, I'll heavily abbreviate that. That's less than or equal to. And it's got a companion greater than equal to. I hope I'm not abbreviating too much. So far we've got is equal to, is not equal to, less than, greater than, less than or equal to, greater than or equal to, 2 ampersands in a row. Again, that is viewed as a single operator, no space between. That means logical and. We've seen and before, but in digital logic, long time ago, not in the context of programming necessarily, with 2 vertical bars, which are somewhere on the keyboard. It feels like it's sort of on the upper right. Sometimes people have trouble finding those. But yeah, upper right of the keyboard, you can find 2 vertical bars. That's logical or. And the exclamation point all by itself is logical not. Got all those operators and no space to work with. You know what? I think I do. I maybe can carve off enough space over here that I can leave that so I can point back at these as I use them. I'll put some examples over here. Carve out a space of whiteboard. Examples. Now suppose we've already set up variables. I'll assume we know how to do that. Variable definitions. We even know how to do assignment statements. And maybe we've already got values for x, y, and z. They're not garbage. They've been assigned to be 9, 5, and 5. That's not relational operators or conditions, either one, but here they are. Here's a condition that uses those, and here's the value of that condition. You know what? I'm going to scoot that back. Condition here, value here, and opposite here. Meaning the logical opposite. When this condition is true, that one would be false. Of necessity. What about this one? Well, x, use this one right away. Double equals y. Let's look and see. Is it true that x is exactly equal to y? Oh, I'm having so much trouble. You know what? This table's in the way. There we go. Is x equal to y? Well, the current value of x is 9, y is 5, so the value is false. F-A-L-S-E, lowercase letters. The logical opposite, I need a condition that's true whenever that one's false, and false whenever that one's true. The logical opposite would be x not equal to y. Now, independent of the current values of x and y, if this condition is true, then that one has to be false. If this one's false, then that one has to be true. And that's what's meant by logical opposite. It means it's opposite in its logical value based on the logical form of the condition and not because of the current values of the variables. How about this? I don't know why I'm looking at paper. I can make these up. Z is less than or equal to y. Well, let's see. The value of z, current value of z is 5. That is less than or equal to 5 because it is equal to it. So that one's true. The logical opposite has to cover all the other possibilities. Well, if z is not less than y, and it's not equal to y, then it must be greater than y. Z greater than y. Notice when you're working with inequalities, especially less than or equal to, all that sort of stuff, there are 3 possibilities that you have to cover. Since this covered 2 cases here, z less than or equal to y, then this one had to cover the 1 remaining one. And how about my next example here? X greater than 9. Well, that's not true. That's false. But when I construct a logical opposite over here, since this only covers one of the 3 possible ways that x could relate to 9, I've got to cover the other 2 with a logical opposite. See how to play this game? So if x is not greater than 9, it's got to be not just this. It's not x less than 9. It's got to be x less than or equal to 9. Why? Why do I have to have all 3 covered for both of those? Well, I've got to have this relationship where if this one's true, that one has to be false. And think about this. Visualize this with me, will you? If x is greater than 9, over here if I have x less than 9, then if x is exactly equal to 9, then both of those would be false. And they can't be logical opposites of each other if they both have the same logical value. So that's not allowed. You can't have this column and that column both true at the same time or both false at the same time. That won't work. What about, let's rope in the logical not down there. I'm going to use a parenthesis, exclamation point, z double equals, what have I not used? Z double equals x. Well, let me see. That one has more than one piece to it here. This is z5, x is 9. Well, those 2 are not equal to each other. So this is true. If we read this in English, it says, it's not true that z is exactly equal to x. You know what? It is not true that z is exactly equal to x, so I've got to write true in the middle column. That looks so complicated. Oh no, how are we going to find the logical opposite? Well, that's easy. Since all I've done is negate a condition, something that's already a condition, all I got to do is unnegate it. So the logical opposite of that is z double equals x. I'm about to run out of board space. I think I can squeeze in one more if I want to. Yeah, how about this? How about z equals 7? Z equals 7. True. Hold up, Poodle Dancer. That's the only place I see a 7 in this entire whiteboard. How could that possibly be true? That's not true. Well, here's a hint, perhaps. I have no idea what the logical opposite of that is. I guess the logical opposite would have to be false. Except that is not a well-formed condition. It's a good chance that's an accident. That's a typo. That should have been double equals. And yet, C++ will trust you as all-knowing programmer. Well, you must have meant to do that because that is not invalid C++. Here's what it does. That's an assignment statement. This says assign B to be 7. I'll draw that arrow for emphasis. It starts on the right-hand side, evaluates the right-hand side, and finds out that's a 7, and makes that the new value of z, changing the value of z to 7, and to ramp things up and make it even worse, now even though z is 7 and the other side is 7, that is still not the reason that condition is true. I like to use the Eskimo religion as a metaphor. They say everything has a spirit in the Eskimo religion. This whiteboard marker has a spirit. The penguin they're going to have for dinner, of course it had a spirit. Everything has a spirit. C++ is similar. It has a similar philosophy. Absolutely everything has a value. So really there's nothing that you can put inside parentheses and force it to be coerced. That's actually the word that's used. If you coerce something that's not a well-formed condition into behaving as a condition, these are the rules. If it's 0, absolute goose egg, then that condition value is false. If it's anything other than absolute 0, positive or negative or anything, then it's true. The reason this condition is true, and I know it's true, is because the value of an assignment statement, its little Eskimo spirit, is whatever value is assigned to the left. Here we go. This statement, in the process of evaluating this as a condition to find out if it's true or false, z equals 7, it sets 7 to be the new value of z, and then it checks to see what the new value of z is. It turns out that's non-zero, so this condition as a whole is true. We've coerced an assignment statement into serving as a condition, and the system views that as true. And you might think, well, that just means every single assignment statement is going to be true. No, that's not true. If I had said z equals 0, even though z started off at 5, 5 is certainly not already equal to 0, but what that assignment statement would do if this had been z equals 0 is make 0 the new value of z, then it would check to see what it just now assigned. That becomes the new value of the assignment statement as a whole, and that would be 0, and that would be false. If that sounds complicated, it kind of is, and that's why you don't want this to happen to you. You know what? I'm going to draw a line through that. You probably don't want to do that in your notes. I'm going to draw a line through that because we generally, very, very often would really rather not do this. There are strange occasions, rare occasions, where you actually do want to put an assignment statement as a condition, but that's beyond the scope of this discussion. In other words, I'm going to put that off till later. I will put a note down here. Let me see if I can have got an alarming red or hot pink. That's pretty alarming. Very different. From a double equals condition. Very different. I don't even think they're first cousins. This assignment statement, it looks perilously like a condition that's testing to see whether or not z is already equal to 7, but it does no such thing. Now, went to all the trouble to write all that down. Now I've got to get rid of that. Oh, I didn't illustrate all of those. Well, I don't have room. I'm going to illustrate some more after I grab some board space here. Even though I erased the title, we will still be talking about logical conditions. Why? Because there's still more to say. Still some more important stuff to say. There. Clean enough. Let's look at compound conditions. C-O-M-P-O-U-N-D. Conditions, I'll abbreviate C-O-N-D'(S). Save what little time I can. These are conditions, C-O-N-D-S, that use double ampersand or double vertical bar. That looks like an 11. That is not 2 ones in a row. That is 2 vertical bars, somewhere near the upper right of your keyboard. A condition that uses, and if you look at the handy-dandy table I just erased, logical and or logical or. A couple of notes, and then we'll look at some examples. Note 1, and I'll represent this abstractly. Pointy bracket condition 1, that is a 1, or pointy bracket condition 2. I'm going to put all of that in parentheses. Why? Because when I combine 2 conditions like that with logical or, that's one big condition. All of that would go into one if statement or one while statement of whatever of the future. That is true, T-R-U-E, whenever. Well, not whenever. I'm going to put if and only if. Sound more mathematical, but that's also more correct. If and only if at least one of condition 1 and condition 2 are true. At least one is true. Excuse my English. Let me read that back and hope I didn't mess it up. See if it makes sense. Got a dog on my foot. All this big mess in parentheses. Condition 1, abstractly represented with pointy brackets. 2 vertical bars, logical or. Condition 1 or condition 2 is true if and only if at least one of these 2 is true. Or both. I'll put that down here. Or both. See, I told you already knew about logical and logical or. That's logical or. 2. I bet you can write this and get ahead of me before I even finish writing this on the board. Condition 1, double ampersand. Condition 2, close parentheses, is true if and only if. Abbreviated IFF. That means if and only if. Both conditions are true. And by both conditions, I mean condition 1, condition 2. I just got a sudden burst of laziness there. Didn't write the whole thing down. Got all that? Let me switch to a different color for the example, because it's not the description anymore. It's an example. Example 1, and that color won't do. I'm sorry. Example 1. There, much better. I better copy this. I might not make it up correctly. Construct a condition that's true. COD for condition. That's true if and only if the value of double, you remember that's a data type that means it's a number that can have a decimal point. Construct a condition that's true if and only if the value of double variable temp, short for temperature, is between 32.0 and 212.0, comma, inclusive. Inclusive means the value of variable temp could be exactly 32, or it could be exactly 212, and we'd still want our condition to be true. Before I even try to write down a condition, just slap it on the board, I'm going to do a few figures. Draw pictures between 32 and 212, meaning it's going to be 32 or more, and then 212 or less, right? So here's some number lines. Here's my number line. Here is 0 way over here, 0.0, and maybe right here is 32.0, and maybe right here is way over here, maybe not drawn to scale, is 212.0. There's my number line. Now, if it's between 32 and 212, there's actually a couple of things that are true. One of them is it's got to be more than 32. And by more than 32, I can represent that on a number line by just making that a double line. I can color it in solid, but I don't want to use up all my ink. So there, it's going to be to the right of 32 on the number line. If it's going to make the value of temp is going to have to be to the right of 32 if it's going to make it true. It's also simultaneously at the same time got to be same number line, same scale, 0.0, 32.0, 212.0. If it's between, I keep saying between, if it's between those two, then not only is it 32 or more, it's also 212 or less. I'll make that a big solid point. It could be 212 or less. Now, if I can find another color that'll work, neither one of those alone is sufficient to test for this condition, to see if temp is between. Try to get some of those out of the way. Between 32 and 212. Because this one is only 32 or greater, this one is only 212 or less. So what I want is a marker that works. That's one thing I want. 0.0, 32.0, 212.0, 212.0. There. What I want is something that is between. So here's what they have in common. I want a condition that tests for that. To see if it is there on the number line. It's between those two endpoints. See how this works, combining those two number lines? This is the number line for temp. It's greater than or equal to 32. Is it not? This number line is for temp less than or equal to 212. So those are my two conditions, condition 1, condition 2. And all I need to do is combine those. I make it sound simple. All I need to do. How about this? Temp greater than or equal to 32. That gets the low end. There's my first condition. Here's my second condition. Temp less than or equal to 212. Second condition, I'm going to have a big set of parentheses around both conditions. Actually, when you type it in, the parentheses will be the same size. But I'm thinking of them as bigger parentheses because they're going to combine those two. And then we get to the crux of the matter. Do I need logical and or logical or? Well, let's think about how we would describe this situation in English. This point right here, let's see, that is two things compared to these two up here. Not only is it greater than or equal to 32, it is also simultaneously less than 212. Right? So all of the points in the shaded area that represent the area that I want tested by this condition, they are all shaded on both of those. These are all points that are simultaneously greater than or equal to 32, and meanwhile, that's a double ampersand. I know I don't write those very pretty, but take my word for it. That's supposed to be double ampersand. I can make that one a little better. This number line represents all the values of variable temp that are greater than or equal to 32 and also simultaneously less than or equal to 212. And ladies and gentlemen, that is a condition we want. That is the condition that's true if and only if. It's true if that condition is true, and only if that condition is true. And you might think, well, the only if, that's just, just trying to say how smart you are and just adding unnecessary exuberance to the description. That's not true. This point over here, 215, whatever, that's true up here. But I don't want the condition as a whole down here to be true up here. I want it true only if it's on both of those numbered lines simultaneously. I want this condition to be true for these points in here and only the points in there. Not any that are on the second one but not the first. Not any that are on the first but not the second. So it's just a very tight, precise way to describe what we want this condition to satisfy. Once again, this is use up the board day. I'm going to get rid of this half because we already know all this now. This is still video I. And also I want to leave that lower condition on the board so we can contrast and compare to something I hope we'll write in dark green. Example 2. You know where this is going, but please join us. Go along for the ride anyway. Construct a condition that's true. If and only if what? Integer variable n is not a single digit integer. If and only if int variable n is not a single digit integer. Single digit integers are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Also negatives. Negative 1, negative 2, negative 3, up through negative 9. So that's how that works. Here's a fig. A set of figs again. First fig, number line. 0 in the middle. 1, 2, 3, yada yada. Up through, I don't know, maybe 9. Then 10. That's the positive direction. Let's do the same thing in the negative direction. 1, 2, 3, yada, yada, yada. Negative 9, negative 10. Now then, let's see here. Whoops, I didn't label them. Negative 1, negative 2, negative 3. Takes a long time to draw that number line. Construct a condition that's true if and only if variable n is not a single digit integer. Well, the easy ones are the positive ones. 0, that's a single digit. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the first one that's not. So what I'm going to do is I'm going to draw an open circle on 9. 9 is not a single digit integer, but anything to the right of it is. I'll make that nice and solid. So there's some of my single digit integers here. Well, actually, that's all the single digit integers. Here's some of the ones that are not. I want the ones that are not to make this condition true. Sounds like there's going to be a not in there. We'll see. I'm not going to label it again, but I'm going to have the same number line with the same markings. I'll at least put zeros marking here. 0, 1, 2, 3, yada, 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 10. Nope, 9, 10. Negative 1, negative 2, negative 3, yada, yada, yada. Negative 9, negative 10. Those last 2 points, those are important on this number line, so I will label those. Negative 9 is the last of the negative single-digit integers when I'm moving to the left, so I'm going to put a circle on that and make it solid go in this direction. There are my 2 conditions. N is the variable of the day. N is strictly greater than 9. Is it not? I don't want greater than or equal to, because that will make it true if n is equal to 9. N is equal to 9 is a single-digit integer, so I don't want to use that one. Same thing down here. This condition is n is less than negative 9. We've got all kind of music playing in the background. So far, so good. Now, let's combine those. 0 in the middle, yada, 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 9, 10. Open circle that direction. That's the first number line. Here's the second number line. -9, -10. Open circle, solid, the dots. I've got my two subconditions already. I'm still trying to get this condition. A single condition is true if and only if n is not a single-digit integer. So here's two possibilities. N could be greater than 9. That's one possibility. N could be less than -9. Put big parentheses around that, and then the moment of truth. And or. Those are my options, combining two conditions. And or. You know what? Don't write this down. Just watch. Look how dumb I am. That was and, so and must work. Let's think about when this condition is true. We just pick a few numbers and see. N is greater than 9. 17. That's greater than 9. That's not a single-digit integer, so that should make it true. Greater than 17. Greater than 9, 17. And 17 less than -9. Well, 17 is not less than -9. So the and condition will be false. In fact, every value that makes this condition true is going to make that condition false, and vice versa. If I move the other direction, go way over here to -20. -20 makes the second condition true, but -20 is not greater than 9. In other words, if I construct it like this, I have a condition that is permanently false, no matter what the value of n is. No matter what. So the and is probably not going to work. Let's think about it. How about we think about it logically, since we're doing logical conditions. Think about this in English. We want this to be true when n is more than 9 as an integer, or there's another way we want it to be true, an alternative, if it's less than -9. You see how it actually makes sense in English? This one, the -20 is going to make this condition true. Why? Because the second half is true, but that's all we need for an or condition to be true. What about that 17? 17 is greater than 9. That's enough. We don't need 17 to be less than -9. Actually, before I changed it, it had the opposite problem as if I used or down here. So look how I can contrast and compare two different color conditions. If I had or here, let's put that hypothetically. Again, don't change your notes, just think about this. Or. One way to think of it is, then temp is a value that's shaded on this number line or is shaded on that number line. Let's think about 500. 500, well, that's going to be shaded on this top number line because it's more than 212. So if I have an or, that's enough. That'll make the condition true because it's, what? Greater, no, it's greater than 32. That's what I'm testing. That's what would make it true. If I had 500, oh my goodness, that's definitely greater than 32, quite a bit. No, did I say 500? Excuse me, pardon me, won't you? I actually meant -500. -500 is going to be shaded on the second number line. How come? Because -500 is less than 212. Where am I headed with this? Absolutely any number you can dream up that's not an imaginary number, it's got to be a real number, it's going to make this condition true. So this one, if I use the wrong logical connective, this is far too liberal. This is going to take anything. This will always be true no matter what the value of temp. If I leave it like that, I'm not going to leave it like that. I'm going to put it back the way it should be. And I want it on both number lines, so it has to satisfy both. It has to be shaded on both, not just one or the other. That one has to be and, this one has to be or. If this one had been and, it would be too restrictive, and nothing would make it true. And nobody would be happy. Okay. One more. I don't have space. I'm up to example 3. Remind me of that when I get the board clear. Example 3. Construct a condition that's true if and only if letter, it's a long variable name, I'll go with it anyway. If and only if this variable name letter, string variable letter is W, comma, case insensitive. I got some explaining to do. There are actually a couple of things going on here. Constructed condition is true if and only if. I want it true only for letter B, W, and not true any other time. String, you might wonder, well, now we've got data type char, why don't we use that? We actually don't use char very often. Even with single variable, even with single letter variables or single digit variables, we will typically go ahead and make those strings. Why? Because it's that good old-fashioned word robust again. If you ask someone to type a letter and they get wild and crazy and type in ABC, it's not going to crash your program if you read that into a string. You'll just test it and see whether or not it's what you want. So string is that way a much more robust mechanism to use for input. If you read even single letters into a string, okay, I've made the case for that. Case insensitive, I haven't talked about that. That just means we want this to be true if it's uppercase or lowercase, either one. Okay, so that should be fairly straightforward and easy. I'll just go ahead and start with big parentheses. You know what? No number lines, no nothing. I'll just write this out. Letter. Be careful. Use double equals. Letter double equals lowercase w or uppercase w. And I erase that whole board for nothing. Done and done. Except it doesn't fit the bill. This condition is always true. Always true. Because again, C++ thinks you are an all-knowing programmer and you meant to do that. Pee Wee Herman style. Yeah, that's what I meant to do. Here are our two conditions. Letter is exactly equal to W. For purposes of argument, let's say letter is actually Z. Well, the first half, that's not true. If letter is equal to string Z, then it's not equal to lowercase w. So the computer tries the second half. There's still hope. Maybe the condition could be true. And sure enough, the second condition is true. That string all by itself is our second condition. It doesn't compare anything to letter over here. And remember, Eskimo religion, everything has a value. The value of this string W is something weird, some ASCII combination of characters, but it's certainly not absolute zero. So this condition is always true. You knew that. Quit messing around. Okay, that's no good. What we meant was this. Be more specific about it. Letter, even use correct parentheses, equals lowercase w, close parentheses, or letter equals uppercase W. There. Fixed it. You know better. You know better. I'm just toying with you. I admit it. Let's evaluate this the way the computer would. Here we come merrily along. We run into this ginormous condition, and the computer wants to know whether this is true or false. It takes string lowercase w and assigns that to string variable letter. Letter is now w regardless of whether it was z or anything else before. Boom, it's true. It's not zero. Why? Because I use single equals instead of double equals. It's not going to see what the value of letter already is. It's going to assign it a new value and then check and see what that new value is to determine if it's true or false. Strike two. So here we go. Two conditions. Letter double equals, for crying out loud, double quote lowercase w, close parentheses, and letter double equals uppercase W. There. Not too hot, not too warm, just right. So here comes the system being the CPU executing your program. It runs into this condition. It's like a fairy tale, isn't it? It's moving down the road. It runs into this condition. Oh, is that condition true or false? Well, it's got to look at the current value of letter. Here's letter. And let's make this a happy ending. It is lowercase w. Oh, look. Letter is equal to lowercase w. Then this is an and. So they both have to be true. Is letter equal to uppercase W? No. No, letter is a variable, and a cardinal rule of variables is they can only hold one value at a time, no matter what. If the value of letter is string lowercase w, even though this condition is true, there's no way that one can simultaneously be true. And it doesn't fix it to make it an uppercase w. If it's an uppercase w, then it's not equal to lowercase w, and it can't possibly be the case that both of these are simultaneously true. Oh. I won't even speak, I'll just write it and then read it back. You're getting so sick of this, I can tell. No, I'll read it. Letter double equals lowercase w, or letter double equals uppercase w. Finally, mercifully, for crying out loud. So here's letter. Let's say it is lowercase w. Comes merrily along. Letter equals, double equals, lowercase w. Well, I'll tell you what, unless lowercase w is a variable that you defined elsewhere in your program, the compiler, we won't even get to run this. There won't be any CPU merrily coming along to evaluate this condition. This won't clear the compiler if that's not a variable, and if that's not a variable, and it doesn't fix it to go back and define string variable w and uppercase w. Because what this is doing is trying to look up in memory the value of a variable named lowercase w. And unless the value of variable lowercase w happens to be lowercase w, that condition won't be true. It's probably not what it's going to be anyway. But this is wrong. This is not checking to see if letter is a w, a literal w. That's got to be enclosed in quotes. Same thing for the uppercase w. In other words, another one bites the dust. And there was much rejoicing among the dogs. I'm going to do one more. I'm switching colors. Maybe there's some significance to that, you suppose? Okay, I'll even write it bigger. Letter double equals double quote lowercase w. That's one way to make this big fat condition true. Or the other way is letter double equals double quote uppercase w. There we go. That parenthesis was just way too big because I need another one on the outside. Big parentheses. Notice there are two open parentheses on the far left, two closing parentheses on the far right. It's because I got two separate conditions in here. The way to make one of the entire condition is true is if we've got a value of variable letter that makes, well, I started to say at least one of those true. In this case, it's only going to be exactly one of these because it can't, as we saw here, it can't possibly make both of them true simultaneously. Okay? Now, yes, that'll do it. There's one more thing I need to say. Well, you know what? I'm not even going to write this down. It's a little more advanced, but it's something that we could very well run into. I'll do an example without writing out the full description, just because this video has gotten so long already. Note, and or, 2 ampersand, and 2 vertical bars are short circuit operators. Meaning they're like me. They're lazy. They're not going to do any more work than they have to do. Here's an example of why that even matters. Example. Double parentheses. If, an if statement. If, we haven't officially covered that. We will in the next video. If, and let's see. If x exclamation point equals. If x is not equal to 0, double quote, no double quote, I can't even read what I'm writing. If parenthesis, x is not equal to 0, close parenthesis, double ampersand for and 16 divided by x is greater than 9. Things get more complicated when I make them up as I go along. And I think I need one more parenthesis over here. What are my two conditions? I've got two conditions separated by logical and. One of them says x is not equal to 0. The other one says this arithmetic thing, that 16 divided by x is greater than 9. What on earth does a short circuit operator have to do with that? Well, the short circuited and says if the first half of your condition is false, there's no reason to look at the second one. Think about that. If the first half of an and condition is false, the whole thing is false. It's a waste of C++'s time to even look at the second one. The waste of the CPU's time. In this case, it makes a big difference. We're testing the water first. We check and make sure x is not equal to 0. If x is not equal to 0, then we divide 16 by x and see if what we get is greater than 9. Why does it matter? If this weren't a short circuit operator, this would crash our program. You can't divide by 0. If you try to divide by 0, it will crash your program and it won't go any further. So this catches it just in the nick of time. We check and make sure x is not 0 before we divide it and see if the result is greater than 9. The flip side of that, the logical or, if the first half is true, it doesn't even look at the second half. So if we get this far, a letter is equal to lowercase w, then it's not even going to look to see if it's greater than uppercase W. It doesn't matter. All it takes to make an OR condition is true is for the first half to be true. Now, that's a lot of stuff. I'm not going to expect you necessarily to have the short circuit operation of our and or relational operators. You don't have to have that down pat until we actually need it for something. But I did want to go ahead and introduce it to you because this comes in, this little trick here of testing the water before you do something real, that is going to become extremely handy when we look at some more advanced features of C++ than we've seen so far. That is quite a mouthful. That video ended up being a lot longer than I thought. So I'm going to shut it off before I do any more damage and say I'll see you online.